Today we are going to begin the direct stiffness approach for computer applications. We begin with slope deflection equations. Consider a prop cantilever under the action of moment m. Then the relation between the applied moment and the angle theta is 4EIL theta. And there is a carryover moment equal to 2EIL by theta. You are very much familiar with this aspect. And using these two moments, we can obtain the reactions, that is 6EI by L square theta. The other system is a cantilever beam under guided roller support undergoing a displacement delta. For this, the required force shall be 12EI delta by L cube, and then the other reaction and the moments can be calculated. You are very much familiar with these two basic slope deflection equations. These two basic equations can be extended into a more generalized form where we derive the classical slope deflection equation. We have a beam with two ends undergoing the displacements delta 1 and delta 2 and the rotations theta 1 and theta 2, for which we have the standard slope deflection equations. From these we can work out the reaction forces F1 and F2, and then if we rewrite these equations in a matrix form, then we obtain something as the stiffness matrix of the member. So our observation is that it's symmetric and the diagonal terms are all positive. This equation can be written in a very compact form. So on the left hand side we have the force vector, which consists of the applied forces and the moments. Whether it's force or moment, we treat it as a force. Similarly, on the extreme right hand side we have the displacement vector. It comprises of translations and rotations, but all are classified as displacements. Now if we extend this approach from member to the entire structure, then what we obtain is the stiffness matrix of the entire structure. For example, consider this frame with 3 degrees of freedom. So here if we obtain 3 by 3 matrix, then that is the stiffness matrix of the entire structure. We can now define some of the terms. First of all, if we have to obtain the jth column of the stiffness matrix, all we have to do is apply a unit force along the jth degree of freedom and find out what are the forces developed along various degrees of freedom. We arrange them in a column that gives us the jth column. Likewise, we can define Kij. So Kij is nothing but it's the force generated along the nth degree of freedom under a unit displacement along the gth degree of freedom, all other degrees of freedom logged. Now we can use two approaches to obtain our stiffness matrix. One is the matrix stiffness approach, where the elements are obtained by first principles using the deformation pattern and by visualization. So here human judgment is a prerequisite. So here we use the first principles and we apply the forces one by one. For example, for this structure, let's say we want to obtain the stiffness matrix. So we will derive the 3 columns one by one. So we have identified the degrees of freedom. Delta 1 is rotation, delta 2 is also rotation, and delta 3 is the translation. So our matrix will be 3 by 3. So we have identified the rows and columns of the matrix. So we begin with the first step, that is we apply a unit displacement along the first degree of freedom, that is a unit rotation along the top left hand joint, and we make sure that no other displacement or rotation takes place, and we use first principles to visualize the deformation pattern, and then we make use of the basic slope deflection equations we have just written down at the beginning. So here the moments at the ends of the two members will be 4EI by L theta. So the total moment required at this joint will be 8EI by L theta. theta being equal to 1, and this will be by definition K11 because this is the moment required along the first degree of freedom when we apply unit displacement along the first degree of freedom itself. So by this definition we are getting K11 and K21 will be the moment at the artificially restrained end. So here we have 8 EI by L as K11 and 2 EI by L as K21. And we can compute K31 also, but let's defer it to the last step, that is involving delta 3. Now let's extend the procedure, and now we apply delta 2 equal to 1 and freeze the other two possible displacements, delta 1 and delta 3, to be 0. So here also we can visualize the deflection profile of the structure, and by following the same logic we obtain K22 as 8 EI by L, and what we do, we again defer the calculation of K32, which is same as K23. We'll calculate in the last step because it is much more convenient. Now we come to the third step. We apply a unit displacement along the third degree of freedom, that is a translation, such that all the rotations, namely delta 1 and delta 2, they are frozen. So here both the columns, they undergo deformation just like the case of a cantilever with guided roller supports. So now this is the use of the second slope deflection equation. So here the horizontal force required to move the structure in this configuration, that will be by definition equal to K33, and by use of the basic slope deflection relations we know that this is equal to 24 EI by L cube. Each column contributes 12 EI by L cube. Our job is not finished yet. We have to still compute K13 and K23, which by definition are the forces along the first and second degrees of freedom when we have applied unit displacement along the third. So these moments we can identify as K13 and K23, and by the basic slope deflection formulations, each of these shall be equal to 6 EI by L square, which we are very much familiar with. So this approach for obtaining the stiffness matrix of the entire structure is called as the matrix stiffness approach. This kind of application is suitable for small and simple structures only, where we visualize. However, it's not practical for big structures. So we use direct stiffness approach. The direct stiffness approach enables computation of the overall stiffness matrix of any structure without any human visualization. It uses the finite element formulation. In this particular course, we will study all aspects of the direct stiffness approach. We begin with simple 2D structures with simple boundary conditions, and slowly we'll introduce complications, and you will be able to obtain stiffness matrix of any structure provided it's a skeletal structure by automatic means by using a computer program. So why we study the direct stiffness approach? Because a lot of now commercial software, they are based on direct stiffness approach. So it's very important that before using any software as a black box, we should understand how it works, what are the basic principles. So if we understand it fully, we'll be able to use the particular software correctly, and we can even write our own program to do things which for example the software may not be geared to do, but we can tweak and we can do the things with our own program. So let's see what are the assumptions of the direct stiffness approach. So first of all, we are restricting ourselves to frame and truss type structures only. Okay, so these are called as skeletal members. So skeletal means that all are represented as line, not as a solid. they are represented as a line, and we assume that all the sectional properties, they are lumped along that particular line only. Okay, next is that at the beginning we are assuming all prismatic members, though later on we will include the treatment of non-prismatic members also, but right now we assume all members are prismatic till we derive the basic formulations, and then we will extend them to all different complicated scenarios. Next, Hooke's law holds good. So that is your stress and strain, they are proportional, and we assume they are connected by linear relationship. So we don't assume any kind of material non-linearity. So we assume materials are linearly elastic. Then we assume that all the deflections, they are small deflections. Why we don't assume large deflections? Because then another kind of non-linearity comes in. Geometry itself might change. Say for example, if we have a structure and we want it to deform under loads, then let's say we have one horizontal load and one vertical load. So this is the deformed structure. Now if you apply the conditions of equilibrium, especially the moment equilibrium, then what does moment equilibrium involve? It involves force multiplied by the distance. Now imagine that the structure has undergone very large deflections. Then what will happen? If large deflections are there, then typically of the order of say 1/10 of the member length are higher, the point of application of the force itself moves. Now you apply moment equilibrium. What will happen? The equations will change. Though the force, they remain same, but because of large deflections, the equilibrium equations themselves, they change. So what this introduces? This introduces another kind of nonlinearity, which is called as geometric nonlinearity. So that's why we assume that we will deal with small deflections only. Typically our deflections could be very small, of the order of 1/100th of the member length. So that means there is no change in the overall geometry. So overall equilibrium equations, they are not disturbed. Number 4, plane sections, they remain plane after bending. So this is a very common assumption. We have used it even in RC design. Then in the bending mode, the slope is very small. Now why this assumption is required? If we have a bending moment diagram and I ask you to calculate deflections, so what method would you use? Moment area theorem, or by first principles you have the curvature, that is second derivative of displacement, you will integrate it to slope, and the slope you will integrate to displacement, something like that. Now what's the assumption there? That truly speaking, our curvature is defined like this. So we assume slope is small, that means your denominator, it can be approximated
to 1.
Yeah. So that's how we use this simplistic relation between curvature and displacement. So we approximate curvature as the second derivative of the displacement. So we assume that slope is very small, that is very large curvature. So that's what we are assuming. Next is that if displacement takes place normal to the member, no change in length of the member. And change in length of the element due to flexural deformation, curvature effects is also negligible. What does this mean? It means very simple terms that if we have a very simple member, just a pin-pin condition beam, that both sides are pin-pin. Now let's say you apply moments at both the ends. Now what is your observation on the length of the member? Has length of the member changed or not? Strictly speaking, if the two ends are fixed and we are forcing a moment, because of the curvature effects, the lengths have to be different. But our assumption is that we are ignoring that if there is any moment effect, then there is no axial force generated. Otherwise, axial force will be generated. And similarly, if displacement takes place normal to the member, then also we assume there is no change in length of the member. That is, let's say we have a guided roller, for example, and we apply a force normal to the length of the member so that the member undergoes displacement. Now, what is your observation? Is there any change in length? Our assumption is that there is no change in length if there is any displacement normal to the axis of the member. So these assumptions are very important so as to decouple the axial force with moment. So axial effects and bending moments, they are independent. Next, we assume that principle of superposition holds good. All linear elastic systems, linear systems, we can do superposition. We can superimpose the loads that we typically do. We analyze for the basic cases and then we superimpose into combinations. Then we can do superposition of the boundary conditions. We can superimpose the displacements, bending moment diagrams, shear force diagrams. Most of the analysis results, they can also be superimposed. So that is our assumption. Now one observation, you have seen the assumptions for slope deflection method or moment distribution method or any of the manual methods. One assumption we have now discarded. What is that? They are just repetition of the assumptions of the slope deflection method. But one assumption is we have discarded. What is that? We have discarded assumption that members are inextensible. We have nowhere said that members are inextensible. Have we said? No. So that assumption we have deliberately discarded. So now we assume that members are extensible. So why we have done it? Or in other words, why do we assume the members inextensible when dealing with the manual methods? While dealing with manual methods, our effort is to reduce the complexity of the problem, reduce the degrees of freedom. So that's why we assume that members are inextensible when solving manually. But here we will not use the manual method. So here we'll use the machine. So that's why we can just discard that assumption regarding the inextensibility of the members. So our members are all extensible. Alright. So basically, what is the basis for the direct stiffness approach? So direct stiffness approach, we assume finite element approach. What is finite element approach? Finite element approach means that we begin with a small element and set up the equations, say compatibility and equilibrium of that element. So element by element we form equations and then assemble all the equations together such that we get the requisite equations of the whole structure. That is finite element approach. All the finite element softwares, they work on that approach. So basically it has widespread applications in various domains. Structural engineering, we can physically see that we have plate elements, we have shell elements, we have solid elements, or we have line elements. So essentially what we do, we begin with one member and we write stiffness matrix of the particular element. And once we have done it, then we obtain the stiffness matrix of the entire structure. So through the process of superposition, such that we get a composite matrix of the whole structure using the individual stiffness matrices. So that is the finite element approach. So we break down the analysis and we form a recursive loop. One by one, each element is processed, various elements of the matrix, they are used. So at the end we obtain the stiffness matrix of the whole structure. So all this process has to be done automatically using computers without involving any human intervention. So the first thing is we have to generate the stiffness matrix of the member. So our member, what is our member? Our member could be truss, our member could be beam. So first of all we deal with 2D case. So the basic formulations we will derive for 2D case and then we will extend it to 3D. We have to define our frame of reference. So we define two different frames of reference, one with the member and other with the whole structure. So we call one as the global coordinate system and the other as the member coordinate system. So some of these in the beginning would be just repetition of what we have learned. It's just a recapitulation. So essentially, how we define the local coordinate system? This is the way we define that our local x-axis is along the length of the member. Now it's up to you which end you choose as the beginning and which end you choose as the end. Doesn't matter. Like here we have from bottom to top the direction inclined, but you can choose the other way also, it's up to you. So we define this is the first joint and that is the second joint, a near joint and far joint or something like that. Now the y-axis has to be normal to the x-axis, and how it has to go such that z-axis should be directed out of the plane of the boat. So whether you assume your x-axis upwards or downwards, you have to accordingly choose the y-axis such that the cross product is always pointing out of the plane of the vapor. So z-axis will always assume pointing outwards. So that is our assumption for the local coordinate system, and we denote the local coordinate system by x dash y dash, and here is the global coordinate system x y. So what we can see is that the z-axis of the local and the global systems, they are matching. So that means if anything is applied along the z-axis, we don't need any change, right, in 2D at least. So now we have 3 degrees of freedom at both the ends, because it's a 2D system, 2D frame for example. We have displacement along the x direction, displacement along the y direction and the rotation. So total 6 degrees of freedom. So our matrix would be like this. Now earlier for the slope deflection we saw 4x4 matrix where we had only the rotations and the translations normal to the length of the member. Now we have other terms, that is axial displacements are also there. So numbering of the degrees of freedom has to be like this, that first is our x-axis, then y-axis and then the z-axis. So there is no force along the z-axis, but there is a moment, so it will come number 3. 1, 2, 3 and 4, 5, 6. So these are the various terms of the stiffness matrix. So all the terms, they are same as the slope deflection method except the new terms EA by L, that force applied along your degree of freedom 1 is EA by L times the displacement when all other degrees of freedom, they are lost. So that's how we have calculated. And actually if the force is here in the positive x direction, the other side it will be minus. So now what we see, our assumption is that the axial effects and the bending effects, they are independent of each other. That's why there is no mixing. So 1 and 4, they are the columns for the axial effects. Another thing is the nomenclature. We are dealing with the local coordinate system, so we'll use lowercase letters to denote the quantities or the parameters for the local coordinate system. So F1, F2, F3, F4, F5, F6, they are all lowercase. So 3 and 6, they are moments, but here we are using the symbol F only. And similar nomenclature holds for displacement. So they are all the displacements, whether translations or rotations, they are clubbed into one, and we use the lowercase d to represent the displacements. So this is with respect to the local coordinate system. So what we can say, we can write in the matrix form like this, that here is the force vector, here is the displacement vector, and we have the matrix 6 by 6. So we use the subscript L to emphasize that it's for the local coordinate system, because local coordinate system we first derive and then we transform to the global coordinate system. Okay, now why do we need coordinate transformation? We need coordinate transformation because we have to enforce two things. One is the equilibrium condition and other is the compatibility condition. To enforce those, we need to transform all the forces of the adjoining members to the same coordinate system. Then only we can do it. At a joint we can have members in various orientations. So we have member end forces. So all the member end forces have to be under equilibrium. Right? Joint should be under equilibrium. So to enforce that, what we do, we have to transform all the member and forces to the same coordinate system. Okay, let's see how we do it. So we have to transform both the forces and the displacements. Even displacements also we need to transform. Then only we will be able to do compatibility enforcement. And similarly we have to transform the forces so that we do equilibrium condition application. So now we have this vector. Vector can be force or vector can be displacement. It can be anything, doesn't matter. So let's say we are showing here the global coordinate system, and let's say we can write the vector in vectorial notation in terms of the components, where Vx and Vy, these are the components of the vector with respect to the global coordinate system. So this is essentially the splitting of the vector into its components. Now if we define another coordinate system which is inclined at an angle theta. So theta is the angle of the local coordinate system with respect to the global coordinate system, and theta could be positive or negative according to our sign convention. Anti-clockwise we assume positive. So theta is positive when it's anti-clockwise. This is our definition of the positive theta. So accordingly all other components might change if theta is the other way. Now we can write the same equations for the local coordinate system also. So let's do that. So vector is same, just that coordinate system has changed. So we say that with respect to the local coordinate system we have Vx dash and Vy dash. Now how do we expand these? Just like here we have done in terms of cos phi, where phi is the angle of the vector with respect to the global coordinate system. Again, this phi also positive direction is the anti-clockwise. So how do we expand this? Just that phi will be replaced by phi minus theta, assuming both are positive and theta is less than phi. So that's what we have done, and now we can expand this. So this is what we get. Now do you find any relation between this and this part? These are family terms now. This is Vx and this is Vy. So now this is the basis for our relationships that we have here. Vx dash, we started with Vx dash and we have broken it down to this expression. We started with Vy dash and we have broken it down to this expression. So that is, we can write them like this, that if we have the components in terms of the global coordinates, we can get the components in terms of the local coordinates. Just we have to bring here theta. And what is theta? Theta is the angle between the local and the global coordinate system. So we can put it in a matrix form like this. So we have cos and minus sin. So essentially we can use another definition. We can use the definition of direction cosines. What is the direction cosine? Do you remember coordinate geometry? And what is the direction cosine? Direction cosine of a vector, what is that? It is the cos of the angles the vector makes with the coordinate systems. Right. So this is what we have. We have the direction cosines of the vector with respect to the global coordinate system. So we have the direction cosines of local x-axis. So this is the making angle theta with x-axis and 90 minus theta with the y-axis. That's why we have cos theta and sin theta. So it is L1 M1. We can use the symbol L1 M1. So these are essentially the direction cosines. So direction cosines of the local x-axis, and similarly these are the direction cosines of the local y-axis. So why we have minus sign here? Because here the angle is
90 plus theta. So cos 90 plus theta is minus sin theta.
So essentially we can write that this can be written as, this matrix can be written as L1 M1 L2 M2. So these are the direction cosines of the local x-axis, and these are the direction cosines of the local y-axis. So in the 3D, when we migrate from 2D to 3D, we'll use the term direction cosines. Right now we are just using theta, but later on we'll use the direction cosines. That's why I have defined it here itself. So this is how we transform the forces or the displacements or any vector from one coordinate system to other. So here we are transforming from global to local. If you know the components in global terms, then we pre-multiply with this matrix we get in the local. So now we have these forces. These are the forces in the local coordinate system. Or these could be displacements. Now same things we can have an equivalent model in terms of the global coordinate system. Now when we come to the global coordinate system, we will adopt uppercase. So remember, in the local coordinate system we are using lowercase, in the global coordinate system we will use the uppercase. And same thing with the displacements. So lowercase d will change to uppercase d. We have already derived the transformation matrix. That is from global to local we have derived. Now one thing you can see that this F3 and this F3 in the local and global coordinate systems, they are one and the same. They don't need any transformation. So transformation is required only for F1 and F2 and nothing else. So let's write the transformation in terms of the matrix we have already derived. So F3 we have 1. We have just kept deliberately 1 and others 0. Third row and third column is basically 0, 0, 1. Because along the moment in the z direction we don't need any transformation. Moment remains same. And same equation can be written for the other end. Right. So we have written these two equations, and now if we combine them we get a 6 by 6 matrix. So what we say, we use the symbol R as this matrix. So now the property of the R is that it is an orthogonal matrix, and if you try to find inverse of the matrix, so inverse will be simply transpose. So that is the orthogonality property of this matrix. That we started with global to local, but then we can very easily go from local to global also. When we are doing the transformation we have to go local to global, right? Because locals are different for different members. So we can write this, we can define this as the joint transformation matrix, that all the forces or displacements at a joint, they can be transformed in other coordinate system using this matrix. And we can write for the other end also, again in the this format, that we are pre-multiplying the global forces or global displacements with R, and we are getting everything in the local terms. So we can combine these and write these in a single set. So we get this matrix, and this is now what is the size of the matrix? It's 6 by 6. And why we have these two diagonal elements as zeros? Because there is no connection. The forces at a joint, they are independent. Just we need the forces at that joint only for transformation. They are independent of the other end. That's why we have zero padding here. So now this complete matrix, we can use the symbol T, and now T we say is the member transformation matrix. So T is basically composed from the joint transformation matrix. So all we have to do is just T we can write as R, R, 0, 0. So R is for a particular joint and T is for the whole member, 6 by 6. So we will be dealing with 6 by 6 matrices to enable all computations. Now same transformation we can apply to displacements also, because our formulations are general. We have now differentiated between forces and displacements. V vector, it could be force, it could be displacement. Right? So we can write this. Now the point is, how do we use it in practical sense? So first of all is that what information do we need to write these matrices? If I give you a structure as a user, so what information do you need to obtain the transformation matrix?
Angle between global and local coordinates.
So the main parameter is the angle theta. So how does the program obtain? If now everything we have to think in terms of the program. Now how many of you have used STAT or any other analysis software? Do you provide theta? So where does it get the theta from? From the exact answer is from the coordinates. From the coordinates. Right. So we have to provide all the joint coordinates. We define all the joints. So from the joint coordinates using the basic trigonometry and coordinate geometry, so program should automatically calculate for each member and should save this information. That gives the orientation of the member with respect to the global coordinate system. And these are basically the direction cosines. The moment we go 3D, then we formally will adopt the direction cosine principle. So this is our transformation matrix, and this also is orthogonal. Inverse, we need not do very hard computations for inverse, just the transpose of the matrix is equal to the inverse. Now let's use it. Now we begin with a member first, because we are dealing with finite element formulations. So we first enforce the relationships for a member. So essentially this basic equation, it includes both the compatibility and the equilibrium conditions for the member. Now we transform it, we multiply global to local, that's how we get, right? And this side also we have just transformed the local displacement in terms of the global and the transformation matrix, and here also. Now we take this on the other side. So we take on the other side, so inverse becomes transpose. So what do we get? By definition, we have the global forces here. By definition, we have the global displacements here. Global displacements means, global forces means in terms of the global coordinates. So by definition, what it should be? It should be the stiffness matrix of the member in global coordinates. That's what by definition. So we use the symbol subscript G to signify that this is the stiffness matrix of the member in global coordinate system. So the program, what it has to do, first assemble the stiffness matrix in local coordinate system. That is standard. This is a standard expression. Then work out the transformation matrix and carry out this computation. So all matrices are 6 by 6 and we'll get the
Stiffness matrix in global coordinate system.
Now let's see for the case of truss. Now in the case of truss, we don't require any rotation, right? Because all the members, they are pinned. So essentially here the unknowns are the displacements, joint displacements. So what will be the matrix for this case? What will be size of the stiffness matrix? 4 by 4 only. 4 by 4, and this is our stiffness matrix. Now the second row is 0, fourth row is 0, because we are dealing with the local coordinate system and member link element, it cannot have any force normal to it. But we have retained, because finally we have to transform in the global coordinate system. So in global coordinate system we will have always x and y components. This force will be resolved into x and y components, so it will have that. That's why we have kept the second and the fourth rows. And this is our joint rotation matrix. So here the matrix will be simply 4 by 4. Because finally we need forces. Let's say when you see the global coordinate system now, the same forces in the global coordinate system. So this is our global coordinate system. So global coordinate system, what is the size of the matrix? 4 by 4. So local we cannot keep 2 by 2. So that's why we have done 0 padding. Otherwise it will be inconsistent. So that's the reason. Okay. So next time now we'll see the basic, we'll derive the basic approach. How do we eliminate manual intervention? So we stop here.